Good morning, everybody, and I hope everybody is fine. And I expect that these videos that I'm working on, these videos will be liked and they'll be shared so that they can reach to more and more people who are interested to have at least some understanding of quantum mechanics and who wish to have some urge to understand the natural phenomenon. Now, the point is that in this video, I'll be talking about Ehrenfest's theorem, and uh, and uh, and this theorem is basically it's showing a connection that we can have under certain approximations, and we can lead the equations of quantum mechanics to the basic laws of Newtonian mechanics. So this theorem, what it states is that the Schrodinger's equations that we are aware about, they lead to the classical laws of motion on an average. The point is on an average. So, if I have to track it down on the in some other way, then this term states that the average motion that we have, average motion of a wave packet, of a wave packet, the average motion of a wave packet agrees with the motion that's corresponding to the classical particle. Now, how can we write down the Newton's second law of motion, or how can we write down the momenta? So, the very first thing we would like to is the time derivative of position is basically momentum by mass. So it's basically momentum is the product of mass and velocity. So this can be one equation, the classical equation that we have here, and the next one is the rate of change of angular momentum. Sorry, the rate of change of linear momentum can be given as the negative gradient of the potential energy. So delta dou V by dou x, if the motion is along x. Or if you have to write down this in all the three dimensions, then instead of using dou by dou x, we can make use of del operator. Now these are our Newton's equations, and we have written down the Newton's second law of motion as a negative gradient of x. You can write it in terms of y. You can write it in terms of z. Now, what is important here is that in quantum theory, what is most gushing thing here is that it's not possible even to define the derivatives of x, y, z, px, py in the classical sense. Can't define them in classical sense. And since there is no such thing basically as a continuous particle trajectory in quantum mechanics, we don't have trajectories, and that's why Feynman called it it's weird. But the results of quantum mechanics are they have a lot of implication. And they appear to be true in most of situations. But at the same time, we don't have any trajectories at the microscopic level. So that's why dealing with these exact derivatives of x, y, z, and all that, we can't do it in the classical sense, because we don't have the trajectory of the particle, which is supposed to be continuous in nature, and the approximate value of the derivative may be found by considering the time rate of change of average value, what we talked about in terms of expectation values. So here you can have you can use these derivatives only in the form of these averages, and at the same time, so when this thing becomes possible, is that if the width of the wave packet that we have here, the wave packet that we have wave packet, what we have to do is we have to neglect its width. Okay, only then the values of these derivatives must be equal to the classically calculated values. So these assumptions ought to be taken in mind, and we can directly go for writing down the expectation value of position. So expectation value of position is it is integral of psi star x psi, and I consider this motion along x, right? And if I take the time derivative of this expectation value, okay, this is going to give me, oh no, this is going to give me d by dt of the expectation value of x. That should be d by dt of integral psi star x x psi x dx. This should be the case. Okay, so if I take this this derivative inside this integral, what I will have is integral psi star then x dou psi by dou x, sorry, dou t, then plus integral of dou psi star by dou t and x y. So what I have done is I have taken this derivative inside, and I have used the UV rule for the two functions. So what we can see here is that we have the time derivative of this expectation value of position is coming out to be this. Now let me call this as equation 1. And let me write down the time dependent Schrodinger's wave equation. So time dependent Schrodinger's wave equation. Okay, what's that? That's IH cross dou psi by dou t is equal to minus H cross square by 2m. Then I have dou 2 psi upon dou x2, then plus v of psi. This is a time-dependent Schrodinger's wave equation, and I would like to get dou psi by dou t, which I'm interested to use in the original equation that I have got for the time rate of change of the expectation of the position. So this is going to be like this is yes, this is 1 by I h cross, and let me keep this thing inside, minus h cross square by 2m. Then I have dou 2 psi by dou x2 plus v of psi. That's it. Okay, this is my dou psi by dou t that I can have from time-dependent Schrodinger's wave equation. And what would I like to do now is to take its complex conjugate, right? If I take its complex conjugate, what am I going to get is I'm going to have minus 1 by I h cross here. So rest, it will be same, h cross square by 2m dou 2, but here I will have star by dou x2 plus here I will have v psi star. So I have this, say, equation 2, and I have this as equation 3. And what am I supposed to do is I will be using the the value of this dou psi by dou t and dou psi star by dou t. That means I'm using equation second and third in equation 1. Okay, so should I call it substituting second and third in 1? Now, in doing so, I would like to keep it here and have it here. Okay, so what am I going to get is, this is number 4. So what am I going to get is d by dt of expectation value of position. Now this should be integral. Okay, what I have psi star, then I have x. Okay, then I will use I'll be using for this dou psi by dou t. So what's that? What would be common is I would like to get that 1 by I h cross out. Okay, that should be out. Then here I will have minus h cross square by 2m, then dou 2 psi by dou x2 plus v of psi. Okay, that should be the case, and then this whole thing is in the integral here. Okay, then I will use another integral for this part, of the equation. So what will that part give me? That will be plus integral of 1 by minus I h cross times that will be h cross square by 2m. Then I will have dou 2 by dou x2 of psi star in this case, and then I will have plus v psi star, and then I would like to close this, and let me have then I will have x in this direction, and then I will have psi dx. Okay, so that should be the case. Okay, that should be the clear version up to now. So what we have is what would we like to do from here now is to get some common term. This is d by dt of x. Okay, now if I manage to get this 1 by I h cross out, and inside what I'm left with psi star x minus h cross square by 2m, then I have the same dou 2 psi upon dou x2, and then what I will have is plus this psi star will be multiplied to this, so this will be v psi star psi. Okay, that should be the case. Then plus okay, then plus what I will have is I have to take care of this minus. Yeah, I have taken care of it. So what am I going to get is here h cross square by 2m, then dou 2 by dou x2, then psi star, okay, then minus v, yeah, that's correct, then psi star uh, and x psi, and then I will have the closure and I will have dx. Okay, that can be verified. You can take minus outside, and you'll get all the signs perfectly fine in this case. Now, what should be the next step that I would like to do here is that 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 moving ahead of it is there any state of you can see that we have a cancellation existing in terms of this v psi star psi and uh, v psi. Yeah, here I'm missing this x. I have to take this x is also with this. Okay, so when this x is with this, then these two terms are gonna to be omitted from this equation. So what we are left with, we should go with that. And so what I will have left is d by dt of expectation value of x is 1 by I h cross. Yeah, what can I do here? I will have this 2m out, and h cross square, and this h and h cross square will go out. So I will have h cross in the numerator as h cross by, yeah, 2m is okay, and iota will also be included. Then what I will have is the integral. It is the integral of what? I am left with psi star x dou 2 by dou x2 psi, then minus psi dou psi star by dou x, and then this whole thing to be multiplied by dx. Okay, that should be the case, and all we know is that this integral is basically from minus infinity to plus infinity. So I can think of writing down this in a more sophisticated way, like if I take this iota up, so this here it should have been minus. Okay, when I take this iota up, it will be plus, so this will be I h cross by 2m minus infinity to infinity. Okay, then I can have this x and dou by dou x of psi star dou psi by dou x, then minus psi dou psi star by dou x, and then dx. Now this should be d by dt of the expectation value of position. Now, if we integrate this equation, the right-hand side of this equation, what we are going to get is, if we integrate it, obviously we have x and we have this whole thing. So if I integrate it, integrating by parts. Now, for that, what I will have is I h cross will be outside, divide by 2m will be outside. Now, this u as it, so I will write x here, then integration of this thing, and when I will take integration of this thing, this differential and integral will cancel. So what I will be left with is psi star dou psi by dou x minus psi dou psi star by dou x. Okay, that should be the case. And then minus integration of differentiation of the first function, that will give me 1. So I'm not going to write that. So this is minus infinity to infinity. And then the integration of this whole thing will give me because this differential and that integral will die. So what I will get is psi star dou psi by dou x minus psi dou psi star by dou x, and this thing is multiplied by dx. There is no dx because, yeah, it has to have a dx of the original integration that's over here. Okay, so that's the case. Now talking about this equation, what limits we have here is from minus infinity to infinity. If we look onto this part of this equation, in this case, if I have x tending to a plus infinity or minus infinity. Okay, so at infinity, psi must be 0. So the value of psi should be 0. That implies at infinity the derivative of this psi with respect to x should also be 0. So immediately I will say that this term of this result that I have obtained for the expectation value of position with respect to time, this result will immediately be equal to 0. So what we are left with is d by dt of x is equal to, yeah, that is, so that part is gone. So what I'm left with is integral minus infinity to infinity psi star dou psi by dou x minus psi dou psi star by dou x dx. Now, this is the case that we have arrived at. You can see that from this equation, what I said is that when I took the integration by parts for this whole thing, the u remains as it's, and the differentiation of this whole thing, integration of this whole thing, the integral and dou by dou x will cancel, and we'll be left with this thing. Now, in this case, we know that this integration is carried out from minus infinity to plus infinity. So when that's the case, then at x the psi should be 0. There should be no value for a wave function at all, and automatically the derivative of this psi will also give us the 0 value. Now, moving on in the same direction, I think I have missed this I h cross by 2m. Now, what would I like to do at this stage is I would like to separate out these two things. So what am I going to get is I h cross by 2m integral minus infinity to infinity, then psi star dou psi by dou x and dx. Okay, then I will have minus. Okay, so then I will have minus psi this is I h cross by 2m integral minus infinity to infinity, and then what I will have is psi dou psi star by dou x, then dx. Okay, so this is giving me the position, the time derivative of expectation value of position. So this is the equation that I have reached till now. Right now, if I talk about this integral here, and I would like to move on with this integral from here, and what am I supposed to do is that 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 I keep on I have to. This is my, okay. Outside I have minus here. So if I have minus here, then I must have minus with this and minus minus plus for this. This should be the case. Now, if we look into now if we move further from here, so I think this is okay. Uh, if we move further from here is let me take this integral now. Now this integral that I have is I will take this part of this integral from this equation, and and what's uh, what's going to happen here is that that this second part of this integral uh, that I have here is what's going to happen here. Yeah, I have psi do psi star and and am I doing it right? I think I'm doing it right, but where am I? This is, did I leave anything out? No, I didn't, because I'm left with an integral. Yeah, I have I have to have this thing. This will give me the integral of, yes. Oh no, what's going on? And this is IH cross by 2m, that's fine. This is psi star dou psi by dou t. Now that's fine. Now, what about this term that I have? If I integrate this, that should be the case. Yeah, because then I can reach. Okay, okay. Now what I will do, I will call this as equation A for the time being, and I will take this integral and I will do integration to this function as, suppose I call this I, and that is I h cross by 2m integral minus infinity to infinity psi dou psi star by dou x, and then dx. Okay, then dx, and let me take the integration in parts for this integral. Okay, so what am I going to get in that case is this I will be equal to, this is page 6 and this is page 7. Okay, so this I will be, yeah, I h cross by 2m. Okay, so what's gonna be the result is so psi as its, now in, now no integration, I'm integrating it, psi as its integration of dou psi star by dou x. That's going to give me psi star, because dou and integral will cancel, and the limit here will be minus infinity to infinity, and then I will have minus integral of then what I will have is dou psi dou psi by dou x, differentiation of psi, integration of differentiation of u times yeah, that will give me what, psi star will remain as it's here, but here we will have the integration. Okay, and then I will close this. I think something has happened. Yeah, yeah. So the point here is, again, in this case of integration, what we see is that that this psi star, because we have to move from what we call from minus infinity to plus infinity. So this term will immediately be equal to 0. So this I that we have will be minus I h cross by 2m integral minus infinity to infinity dou psi by dou x, yeah, and then psi star dx. That should be the case. That appears to be the thing till now. So if I that seems to be the case. Now if I think of getting this I h cross inside this integral, then certainly I'm going to find the changes. Now I'm going to use this integral that I have in the original equation. So what should I call it? I should call it b. So substituting b in 1. So substituting b in a. Okay, so what will I have is d by dt of x will be equal to, okay, minus I h cross by 2m integral minus infinity to infinity psi star dou psi by dou x, and then dx. This is the first term. The next one will be this. Okay, what's that? That is minus I h cross by 2m integral minus infinity to infinity dou psi by dou x, then psi star dx. I don't know, where am I? Okay, that should be fine till now. Okay, now if I see this equation closely, what am I having is what I have is psi star dou psi by dou x, psi star dou psi by dou x. So you can add them, and when you will add the two, this 2 and that 2 is going to cancel, and we will be left with the single term. So this is 0.8. So what we will have here is d by dt of x will be equal to, yes, so this will be minus twice I h cross by 2m integral minus infinity to infinity, yeah. Then what you have is this psi star dou psi by dou x and dx. So this 2 and 2 is going to die. So what we are left with is dou by d by dt of x is going to be, what is it going to be? Let me have 1 by m inside and integral minus infinity to infinity, and this psi star here, and bring this this I h cross inside, minus I h cross, or you can call it h cross by I dou psi by dou x and dx. Now, as we know that the momentum operator is h cross by I dou by dou x. So here, what we have is d by dt of x is equal to 1 by m. Now this is integral minus infinity to infinity psi star and momentum operator psi dx. Now what is this? This is the expectation value of momentum. So I think we have achieved one result, that is for the momentum. So what we have is is that this d by dt of x is average value of p by m. So that's the first thing. And if I go with the with the equation for momentum that I have here, now what does this d by dt of x represent? Is basically it is representing the momentum operator divided by mass. the expectation value of momentum divided by mass. Now, if I go with expectation value of momentum, and what will be the expectation value of momentum, and I would like to change it because my intention is to have Newton's second law of motion. So I would like to have the derivative of expectation value of momentum. And what will be that? That will be d by dt of integral of minus infinity to infinity psi star minus ih cross dou psi by dou x, and then I will have dx here. This will be the case, and I will integrate it with respect to time. So I would get minus ih cross out. So integral will stay there. Then I will have psi star as its into the time derivative of dou by dou t of dou psi by dou x and dx, and then I will have plus integral of the differentiation of dou psi star by dou t, and dou psi by dou x will remain as its, and dx, and this whole thing should be closed under brackets. Okay, so that's the case. Now what can I do here is that this minus ih cross, I would like to write it in the same way, and I would like to write down another step. This is psi star. Yeah, this is psi star. What? Then dou by dou t of dou this is dou psi by dou x. Okay, that's correct. So here I have a separate dx, and then I will have I will have this plus, and I will take that minus ih cross into another integral. So what I will have here is minus ih cross dou psi by dou t, and then I will multiply this with dou psi by dou x, that's here, and this is to be multiplied with dx. So I do have these two separate entities, and moving from here and using the approximations that we have used in the previous case, then what will we get here is that we will have integral, that should be psi star, yes, dou by partial derivatives are commutative in nature, so dou by dou x ih cross dou psi by dou t dx will be the first case, and the next thing I will have is plus integral of minus ih cross dou psi star by dou t, and then outside you will have dou psi by dou x, then dx. Now we can see that for these two equations, for these two parameters, if I think in terms of Schrodinger's time-dependent wave equation, and now if I would like to write that is minus h cross square by 2m, then I have dou 2 by dou x 2 psi plus v of psi is equal to, that's equal to what? That's equal to I h cross dou psi by dou t. Okay, so we can have its complex conjugate. So for this I can use this in the above equations, right? So what am I going to get? In the left hand side I have d by dt of expectation value of momentum, and this is from minus infinity to infinity. This is minus infinity to infinity. So what you will have here is minus infinity to infinity. Then you will have psi star, and then what you will have, this is dou by dou x, and then what you will have this whole thing minus h cross square by 2m and del 2 psi upon del x2 plus v of psi, v psi, okay, v psi. Then we will have dx, okay, and then we will have, for another part, I will have plus minus infinity to infinity. And for this, again, what am I going to use is the complex conjugate of this equation, right? So when I will take the complex conjugate of this equation, what am I going to get is that the same thing, minus h cross square by 2m, then dou 2 psi star, here I will have by dou x2 plus v psi star, and then I will close it by by what, dou psi by dou x, and then dx here. So this will be the result by substituting for Schrodinger's time-independent part in these parentheses, where I'm making use of Schrodinger's time-dependent equation and putting the value of IH cross dou psi by dou t in the above parameters, for dou psi by dou t, and then for dou psi star by dou t. Now, this way, what we have done, we have used Schrodinger's equation, and we can carry out the same analysis of integration that we did in the first part, and the similar boundary conditions can be used, and where you will find, it will be a part of assignment for you. You will find that these bunchy integrals will die out at x plus minus infinity, and what we will come up with is that we will have d by dt of p, which is basically along x, that will be minus integral of psi star dou v by dou x psi and dx. Now, this thing is a representation of average value of change of potential energy with respect to x. So I can write d by dt is px, that's equal to the expectation value of minus delta v by delta x. So you can see that we have achieved both the parts that are linked with the Newton's classical equations of motion, but the results that we have obtained here are in terms of expectation values. So I should say that this equation and the equation that I obtained for position d by dt of r of x. Yeah, what was that? That was expectation value of momentum. That has to be expectation value of momentum along x, because we have carried out everything along x. So that's why the results obtained here are along x. And if you'll carry the same analysis along y, you will get the same thing for y. Then you will get same thing for z. So we can generalize them in generalized terms, and we can say that this d by dt of p is it is expectation value of minus gradient of v. Okay, and the next part will be d by dt of r. That d by dt of r will be equal to the expectation value of momentum divided by mass. So this is how we are in a position to realize that that classical physics, the classical mechanics, is purely an approximation of quantum mechanical description of the wave packets associated.